Okay, before we head into our next section of calculus, we need to do a little throwback to Algebra 2 and talk about inverse functions and kind of the link in calculus back to inverse functions. This is something that comes up on the AP, and it's not necessarily a calculus idea. It's an Algebra 2 idea based on knowledge of inverse functions, but it can look way more complicated than it is, just simply because of the calculus notation. Like the question they're asking you isn't a calculus question, but the notation is very calculus-y, and so it can look a little bit intimidating. So I want to talk to you today about inverse functions and what they are. You may remember from Algebra 2 that inverse functions undo one another, like the two I have in front of you here. Our friends, the square and square root. Right? You take a number and you square it, and then you take the square root. Theoretically, you get the same number back, right? If it's a negative, there's a little, when you do the square root, it's technically a plus or minus. But the general idea is that inverse functions undo one another. They're like inverse operations. Okay. In Algebra 2, you talk about how to find an inverse function. And what we talk about is that the graph of an inverse function is very simply a reflection over the line y equals x. When I taught Algebra 2, I used to have the kids graph a function, and then we would actually fold the paper on the diagonal and see how they line up on top of each other. But the way that that fleshes out is literally that if you have a function and you take the x values and the y values and you just switch them, you now have the inverse function. A switch of x and y graphically creates that reflection over the xy axis when you trade x values with y values. Okay. So in Algebra 2, what we learn is that if you have a function and you want to find its inverse, the basic idea is that you take x and y physically in the equation, you switch places, you replace all the x's with y's and all the y's with x's, and then you solve for y again. And what that does is it gets you a new equation where x is solved for in y of terms of x, but it's the flip-flop version. So for example, here, 5y equals x squared, and I want to find its inverse. Instead of writing y, I write x, and over here, instead of writing x squared, I write y squared. And if I then solve this equation for y, I get that there's actually two functions that are required to create the inverse of this graph. Now, I'm only looking at the positive values here, so I'm going to stick to positive values over here, take the square root of both sides, and you get the square root of x. Now, this is a really easy one to do that to. They're not all that easy, right? Okay, so in Algebra 2, I called this the old switch and solve, because I thought it was funny, and it is. The general idea is this, that if you have a function that contains the point AB, so I don't care, anywhere up here, it contains the point AB, so f of A is B. Then on your inverse function, you are going to have that exact opposite point. In other words, f of B will be A, or you will have BA. So, and again, I keep saying Algebra 2, but it would look like this. In the function table, the point would be AB. In the inverse table, the point would be BA. Okay? They're flip-flopped. And we know that that is a fact about inverse functions, so that if you know a function is an inverse of another function, you know that that's true. Any ordered pair you have on one, if you flip-flop it, it's on the other one, and that's going to become very important to us, because what we need to talk about isn't just the points on an inverse graph. We want to talk about their derivatives, right? We're going to start talking about the calculus of it. But again, notice here on this graph, y equals x squared, the point 24 exists here. On the other side, notice the point 42 exists. Over here, the point 39 exists. Guess what's over here? The point 93. It's just a flip-flop of x and y. I need to carry that into calculus and see what the implications are for slope. Okay, so if we take a look at these same two graphs and we start talking about their slopes, now we're talking about derivatives. So if I take the derivative of y equals x squared, that's 2x. Right? So it's pretty easy to find the slope of this graph at any given point. There's my 2 points I was talking about before. Right? So at the point 2, 4, my slope is going to be 2 times my x value, which is 2. So 2 times 2 is 4. Okay. At the 0.39, again, my slope is just going to be 2 times my x value, or 6. Okay. Let's take a look at the inverse function. If I take the derivative of the inverse function here, it's a little bit more complicated of a derivative, but not too terrible, right? Notice my notation here. Prime notation just went out the window, right? Because I have this to the -1 up here indicating inverse. So now I can't write prime. So here we are back to the why would you ever use dy dx notation? Well, here's a reason. You can't write y inverse prime. That spot's already taken. So there's a lot of notation that kind of comes together in that exponential spot there. It could be an inverse, it could be a derivative being indicated up there, or it could be a power, something as simple as a power being indicated up there. So depending on what we're looking at, we have to be really careful with notation. So in this case, we never, ever, ever are going to use prime notation. So down here, I have the derivative of y inverse. So that's going to be 1/2 x to the -1/2, which simplifies out to 1 over the square root of 2. So once again, let's take a look at the slopes at these 2 points. The 0.24 became the 0.42. My slope, here's my equation for my slope, but now my x value is 4. So my slope on this graph at the 0.42 is going to be 1 over 2 times the square root of 4, also known as 1/4. At the 0.93, my slope is going to be 1 over 2 times the square root of 9, because 9 is now my x value, also known as 1 over 6. You may notice something. I'll give you a moment. All right, so let's think about this for a minute. Let's think about this for just 1 minute. Let's go back to the algebra definition of slope. The algebra definition of slope is change in y over change in x, right? So for this function, if I want the slope, let's say I'm finding the slope between these 2 points. I'm going to take this y difference and I'm going to take this x difference and I'm going to divide them out. Well, what happens when you switch x and y? When you switch x and y, your x distance becomes your y distance becomes your x distance. In other words, your slope, instead of being change in y over change in x, these values, the change in y is now your change in x. Change in x is now your change in y. So the effect is that your slope literally flips over, because what used to be your change in y is now your change in x. What used to be your change in x is now your change in y. So your delta y over delta x, in the inverse, the slope is still defined as delta y over delta x. It's just that the values of them have switched, right? So in the inverse, my slope goes like this. And I end up just getting the reciprocal of it. So if I have a point over here, and I know that at the point AB I have a slope of k, I know that on my inverse, 2 things. One, I have the point BA. That's algebra 2. If you had the point AB over here, now you have the point BA. What we're adding here, the calculus level, is that the slopes are now reciprocal. So if you know the slope over here, you also know the slope over here. If you know one, you know the other. Okay, are you ready to see what that looks like in calculus? The notation of this is absolutely just, I'll just show it to you. Let's just do it. There it is. It's fine. So look what this is saying. This is saying that the derivative of a function at some x value a. So in other words, this is the slope at a. So this is the slope at this point, right? They're calling it c. I called it k up here. So they're saying the slope of a function at a is c. Well, that means that if you go over to the inverse function, the slope at that kind of corresponding part, but notice it's not the a value anymore now, it's the b value, right? Because my a and b have switched. So now instead of the input being A, the input is B because I'm on the inverse. And notice that the slope switched. This is an extraordinarily fancy way to say that if you have an inverse, the X and Y makes a flip-flop, and so does the slope. That's it. So again, you can see how the notation of this makes it look a heck of a lot harder than it is. These should be really quick 2-second questions, but people tend to try to get hung up on them, either thinking, I don't know anything about the inverse function, when actually you do, or trying to actually find the inverse. If you're actually trying to find the inverse, you may be going down a very long road. All right, so obviously, let me move my floating head over here, because obviously we're going to do this in terms of smiley faces. I think it's smiley faces and sunshines and hearts, because I'm feeling very happy and sunny today. All right, so look at this graph. I have for you a graph of f of x, the red one, and a graph of g of x, the blue one. And we have defined that g of x is the inverse of f of x. So these are the types of statements we're looking for. When you see a function defined as the inverse of another function, this whole kind of connection should jump into your head. Also, defining a function as the inverse of another function is really going to help us with notation. Because now, if I want to talk about the derivative of the inverse, I can just write g prime. I don't have to write d dx of f inverse of x, because that's a lot. It looks like a lot. But if you just define the inverse and give it a new name, now you can just write g prime. So that's nice. Okay, so again, notice, hearkening back to Algebra 2, here's your line y equals x, and notice that g of x is just a reflection of f of x over that diagonal line. All right, so I'm going to define a point on f of x. The point I'm defining is smiley face sunshine. Doesn't matter where it is. Right? The fact is that if the point smiley face sunshine is on f of x, then on g of x, I promise you, there's a point that is sunshine smiley face. So if I tell you that f of x has the point 2, -10, then that means that you immediately know that g of x has the point 10, or -10, 2. Okay? It's just a flip-flop of x and y. If I tell you that f of x at that point has a slope of heart, you immediately know that the inverse has a slope of 1 over heart. Again, at that corresponding point. So if you find yourself in an inverse situation, I want you to try to remember this. This is the big connection, and again, it's not a calculus connection. It's Algebra 2. The only thing calculus here is the notation. I find all of this very difficult to keep track of in my head, so you'll notice as I do these, the first thing I do is I write f of x and g of x, and I write down my point and my slope, and then I switch them and write them down on this side so that once they ask me a question, all I have to do is go back to what I already wrote down and figure it out. All right, let's take a look at a couple. All right, now I have to move my head again. Oh wait, no I don't. It says f of x is continuous on 1 to 5. So that's going to be important to us because if the function isn't continuous, if you have a discontinuity, that means you don't have a derivative. That's no good, right? So this is kind of a CYA statement that they have to make, that it's continuous on the interval from 1 to 5 since they're giving us data. We know that none of these are discontinuities. All right, so let's go through these one at a time. So it says f inverse of 3. So again, this isn't a calculus question, right? That's f inverse. They're saying, what is the y value for the point on the inverse that has an x value of 3? So for me, I would go, all right, well, I have a function f of x, and I have a function f inverse of x. You're telling me that on f inverse of x, there's a point 3 comma something, and that something is what you're looking for. Okay, well, that means that on the function, there must be a point something comma 3. Because I know this is true about inverses. If this one has a point 3, let's call it A, then this one has a point A3. So if this one has the point 3 question mark, then this one is question mark 3. Look what I have. All I have to do is go to my table. There's that point. Here's the point I'm looking for. If the point 5,3 is on the function, then the point 3,5 is on the inverse. Therefore, f inverse of 3 has to be 5. Right? It can seem a lot harder than it is. You just have to be aware of what inverses are. Right? Now, this question, this is a calculus question. They look very similar. This is saying, hey, what's the derivative at 3? And it's the derivative of f. So for this one, all I have to do is go, okay, well, let me go, I need f, right? This is f. Let me go to 3. The derivative of 3 is -2. Done. So this, the whole key here is looking at the notation. All right, let's take a look at another one. All right. Again, let's break this down. I want the derivative of f inverse of 10. So, again, I'm going to write my f of x and my f inverse of x. They want f inverse of 10. So they're telling me that on the inverse, my x value is 10. I don't know my y value. But I do know, though, if I go back to f of x, if this point has, if f inverse has a point 10 question mark, then f of x has a point question mark 10. So let me go see if I can find that point. There it is. So f of x contains the point 210. That means f inverse of x contains the point 10, 2. So f inverse of 10 is 2. I want the slope at that point. Well, I know that at 210, the slope is 4. So I know that at 10, 2, on the inverse, the slope must be 1/4. And there's my answer. Again, it is very helpful, at least for me. I'm not good at keeping track of stuff in my head. Write down what I know, and then see if I can translate it over into the other column. It's always going to be a back and forth. They're going to give you a function, but ask you about the inverse. Or vice versa. All right. Okay. Same thing, but with a different value. So again, let's write our columns here. All right. F inverse of 3. So again, I have a point that's 3 something, which means over here I have a point that's something 3. Let's go find it. Something 3. There it is. So if this function has the point 5,3, then this one has the point 3,5. So now I know what my question marks are. Over here, they told me my slope is -1. So over here, my slope is just the reciprocal of that. So 1 over -1, also known as -1. So it doesn't necessarily look at a glance like we did anything, but we did. We did the reciprocal. All right. F inverse of 4. So again, same thing, right? Let's do our columns again. I've got f of x and f inverse of x. F inverse of 4. So I know I have a point 4 comma something. That means over here I need something comma 4. Let's go find it. I don't have it. I don't have it. Don't start making stuff up at this point, right? We do not know. We don't have a point with a y value of 4. Therefore, we can't figure out what the y value is over here. Do not make the mistake of going here. Do it, right? This is 4, 6, which means this would be 6, 4. It's not what we're after. Right? So you can't do one like that. Whatever you do, don't just go to the table and look for a 4 and try to find it. Right? They're going to put, like I did here, see I put a 3 in 2 spots? They're going to do that, and they're going to see if you go for the wrong one. Or they're going to say, find it, or explain why you can't. Right? And you definitely want to be really careful. Keep an eye on the x's versus the y's, especially when it comes to inverses. Okay, last one, f inverse of 6, and I want the slope. So again, if my inverse is 6 something, then I need something 6. Where is it? There it is right there. Okay, so this one has the 0.46, so this one has the 0.64. Over here, they told me my, Over here, they told me my slope is 0, so what does that make my slope over here? That's a reciprocal of that, 1 over 0, which is undefined. Think about this. If you have a function that has a horizontal tangent, if you do a reflection, that horizontal tangent becomes a vertical tangent, which is a no-no for derivatives. So this derivative doesn't exist. If we go back, actually, to... Oh, actually, you can see it right here. This function f of x has a horizontal tangent right there. Look at g of x. Vertical tangent. Derivative is going to fail to exist there. Same thing happens here. I have a horizontal tangent right here. Over here, that same spot at 0, 0. When you flip x and y, 0, 0. Over here, the slope is 0. Over here, it's 1 over 0, or undefined. I did not mean to do that. Okay. Let me get back to my life here. Okay. All right. So this is kind of the way we see this on open-endeds. Again, you can see this. We see these all the time, just like really quick, one piece of a question. They're pretty common multiple choice, but they're pretty easy to see as just one point of an open-ended as well. So notice here it says let y equal, f of x equals, so y is f of x, yes, we know that, x cubed plus x minus 2. Why do I feel like there's a typo there? Why do I feel like there's an exponent missing and like maybe that should be an x squared? Let's go with it. I feel like there's an exponent missing there. All right, and let g be the inverse function. Now I want you to notice what they've done here. They are forcing you to know the calculus connection. And here's why. If what you try to do here is say, oh, okay, well, I'll just find the inverse and then take the derivative. Have fun trying to find the inverse of this. Okay. If you try to take the inverse of this, it's x, y cubed, y squared, y d. So you could then do implicit differentiation, and you're going to spend a really long time working on this problem. Okay. Or you could just do the old switcheroo and take your knowledge of inverse functions and apply it here. Okay. So look, I need g prime of 0. So here's f of x. And here's my inverse that we're calling g of x. Okay, g is the inverse of x. So they want g prime of 0, so they're saying the point 0, comma, something. All right, that means over here we have something, comma, 0. So I need to figure out what this value is. What I really want is the slope, right? So let's find the slope of this function. So over here, y prime is going to equal to 3x squared plus 2x plus 1. And then over here, I know it's just going to be 1 over that. So over here, my y prime, or my g prime, is 1 over this. So if I can find out numerically what my x value is here, all I have to do is pop it in here and then flip it over. And I'll have my inverse function's derivative at 0. All right, now for this function, in order to figure out this x value, I need to take this thing and set it equal to 0, right? So I need x cubed plus x squared plus x minus 2 is equal to 0. Now, they're going to have to either give you the graph of this so that you could pull the 0 off or label the point, or it's got to be a calculator question so you can find the 0, because this isn't something that we are algebraically going to be able to solve. I was just seeing if I could factor by grouping, because that would be so fantastic, but it's not a factor by grouping. It would be so close, but it's not. It's not. So you do, in this case, since we don't have a graph, I went ahead and made the graph, and you have to find the 0. So the 0 looks to be just shy of 1. So I'm going to do a little calc. Say, find me the 0. It's somewhere between 0 and 1. I can see that on my graph. It comes out to 0.8105357. Now, I think I've said this to you before. It's worth noting again. 0.8105357. I am under no circumstances doing a calculation with this number. I'm going to store that number in my calculator because I need to always make sure that my final answer is accurate to 3 decimal places. In this case, you'd probably be okay, but you don't ever want to take a chance. So what you want to do with a number like this is right above your on button down here, you have a store button. As you have that number up on the screen, hit store. You got to quit out of your graph, sorry. Hit store. It's going to say ANS with an arrow. And then pick a letter, any letter. I like to pick A because it's right underneath the alpha key. So in order to use those little green letters, I have to hit the green alpha key and then the A. So I'm going to store it as A, and then you'll see the number pop up on your screen. So I don't know if you can really read that very well or not, but you'll notice that I said store as A, and then when I hit enter, that decimal came up. So the calculator is storing not only the numbers it's showing you on the screen, time for class, but also storing them all. So now I know this number. Now I'm storing it, so I'm only going to write down a few decimal places. But when I do my calculation, I'm going to use them all. So I'm going to go into my calculator, and I'm going to do 3 times that number squared plus 2 times that number plus 1. And that's going to give me my slope here, which is 4.5919, blah, 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 blah. I'm not writing the whole thing down, but I sure am going to use it in my calculator. I'm going to hit inverse, because that's going to give me the number I need for over here. And that is 0.217 or 0.218, because the next decimal place here is a 7. So AP allows you to either truncate, meaning just cut off, or round. So both 0.217 and 0.218 would be acceptable here. Okay, let me know if you have any questions on this, and we will talk later. Happy Inverse.